The right hand side of this differential equation is a unit step function. And to solve this one using the Laplace transform, we will have to take the Laplace transform on both sides of this differential equation, and that means that we will have to take the Laplace transform of this unit step function. Alright, so let me remind you about some of these things before we move on to the question. So the Laplace transform of the first derivative, that's y prime of t, this is s times capital Y of s minus y of 0, the initial condition. And this is the Laplace transform of y of t. The Laplace transform of the second derivative, which is y prime prime of t, this is s squared times capital Y of s minus s times y of 0 minus y prime of 0, like this. And now the Laplace transform of this unit step function, if we can recall. So the Laplace transform of a unit step function shifted at a, changes the behavior at a. This one is equal to e to the negative as. This one is divided by s. So this one, you can watch my tutorial on the Laplace transform of unit step functions. So to keep this in mind, we will now have to take the Laplace transform on both sides of this differential equation. So now let's do that. So the Laplace transform of y prime prime of t plus 2 times y prime of t, right, plus 5 times y of t. And this is equal to the Laplace transform on the right hand side, which is ut minus 2, like this. Cool. So now on the left hand side, applying the linearity property, that is going to be the Laplace transform of y prime prime of t plus 2 times the Laplace transform of y prime of t, like this, plus 5 times the Laplace transform of y of t. And this is equal to the Laplace transform of the unit step function, which is u of t minus 2, like this. Cool stuff. So now let's apply this. So now we are going to replace the Laplace transform of y prime prime of t with what we have here. So that one is s squared multiplied by capital Y of s minus s times y of 0 minus y prime of 0. We are done. Plus 2 times the Laplace transform of y prime of t. And y prime of t is that, the Laplace transform. So s times capital Y of s minus y of 0. Plus 5 times the Laplace transform of y of t, that is simply capital Y of s. And this is equal to the Laplace transform of the unit step function. This one is e to the negative as all over s. And a in our case is 2, the value upon which the function will change the behavior. So this is e to the negative a in this case is 2, so 2s divided by s, like this. Cool. So now let's simplify this. With the initial condition, we have y of 0 is equal to 0, but y prime of 0 is equal to 1. So this one is 0. So this is s squared capital Y of s. This is 0, but this is 1. So this is going to be minus 1 plus 2 times s times capital Y of s. 2 times 0 here is going to be 0. And now we are going to add 5 times capital Y of s. And this is equal to e to the negative 2s all over s. Cool. So now let's gather like terms. So let's put I'm going to factorize y of s out. When I do that, I'm going to be left with s squared plus 2s plus 5, like this. And now this one is going to be minus 1, which is equal to e to the negative 2s all over s. So now let me take the 1 to the right hand side. So now this one is going to be positive 1 now. Let's do everything in one line. So now to isolate y of s, we will have to divide both sides by this guy. So that means that y of s, this is equal to e to the negative 2s. This is divided by s, and then s squared plus 2s plus 5, like this. And now plus 1 all over s squared plus 2s plus 5, like this. Okay, so now the the solution to the differential equation is going to be y of t. How do you get y of t? To get y of t, we'll have to take the Laplace inverse. So let's go back to the t world because we want our solution in terms of t, and that implies that we are going to take the Laplace inverse. So let me do it here. So we are going to take the Laplace inverse on the left hand side, and on the right hand side we are going to take the Laplace inverse as well to maintain equality. So on the right hand side, let's apply the linearity property of the Laplace inverse. I'm sorry about this. So the Laplace inverse of capital Y of S, that is going to return our solution in the t world, y of t, and this is going to be the Laplace inverse. And now applying the linearity property, e to the negative 2s, this is divided by s into s squared plus 2s plus 5, like this. And now the next one is going to be the Laplace inverse of 1 all over s squared plus 2s plus 5, like this. So the headache now is to find the Laplace inverse of these guys. I think the second one is relatively easy, so now let's do that. So the second one, let me call this one L1 and call this one L2, and when I get them, let me call this one equation star. When I get them, I'll just come back to equation star and then put them together, and that will be the solution to our differential equation. So let me do this the second one first. Second one is relatively easy. We'll do that in yellow, why not? So L2 is the Laplace inverse of the second one. So L2, this is the Laplace inverse of the second one. So this is 1 all over, I'm going to complete the squares of the denominator, and doing that, that is going to be s plus 1 all squared. So this is not a denominator because s plus 1 all squared, this one is s squared, that is foiling s squared plus 2s plus 1, but it is plus 5, not plus 1. So what I can do is to just add 4 to both sides, plus 4. So that means that s plus 1 all squared plus 4, this is the same as s squared plus 2s plus 1 plus 4 is 5. So in place of s squared plus 2s plus 5 at the denominator, I'm going to write s plus 1 all squared plus 4. And 4 can be written as 2 squared, like this. Alright, cool. So now let me clean this. This was just by way of illustration. Cool stuff. So now let me close this. I'm sorry, this will be a yellow pen. Alright, cool. So now this is what we have after completing the squares of the denominator. And now this one looks like the sign of something multiplied by an exponential function. But we have 2 squared at the bottom here. We need to have 2 on top. There is no cause for alarm. What I have to do is to just remove this one and replace the 1 with 2, and then take the 2 away by dividing the Laplace inverse by 1/2, by multiplying by 1/2, I mean. So now after doing this, this one is something that we know. Let me do something here. The Laplace transform of this e to the negative t, right, multiplied by sine of 2t. This one is equal to, this one is going to be 2 squared. So 2 divided by s squared plus 2 squared, like this. But we are going to evaluate s at s to be equal to -1. So that's, replace s with s plus 1. So it's going to be s minus -1. That is, you are shifting the s variable by -1. So s minus -1. So this one is going to be 2 all over s plus 1. Replace s with s plus 1 squared plus 2 squared, like this. So you see that this one and this one are the same, right? So this one is the Laplace transform. So the Laplace transform of this guy is what we have there. So this one is the Laplace transform of e to the negative t multiplied by sine of 2t. So this one is 2 divided by s plus 1 all squared plus 2 squared. That means that if you are taking the Laplace inverse of 2 divided by s plus 1 all squared plus 2 squared, this one is going to return e to the negative t multiplied by sine of 2t, like this. So this one, the first one, is just the Laplace inverse of this, and that is just e to the negative t. So L2 here is going to be 1/2. This is e to the negative t, and this is multiplied by sine of 2t, like this. Cool. So this is the first shifting theorem of the Laplace transform. All right, so we have gotten L2. Now let's go to L1. L1, we will have to use partial fractions to solve that. So let me do this in a different color. Let me use green. So L2 is the Laplace inverse of something like this. Laplace inverse of e to the negative 2s, right? Right. All over s into s squared plus 2s plus 5, like this. And this one, let me remind you, this one is something like this. So if we have the Laplace transform of a Heaviside function, Laplace transform of u of t minus a multiplied by f of t minus a, right? The Laplace transform of this one is going to be e to the negative as multiplied by the Laplace transform of the unshifted function. So that means that if I'm taking the Laplace inverse of e to the negative as multiplied by the Laplace transform of the unshifted function, the Laplace inverse of this is going to return the Heaviside function or the unit step function, u of t minus a multiplied by f of t minus a. So if I'm taking the Laplace inverse of something involving an exponential function e raised to the power negative 2s divided by a certain function, this one is going to be like this. Alright, so L2, this one is going to be, which is the Laplace inverse of this guy. This one is going to be a unit step function multiplied by a certain function shifted by a. Right, so the unit step function is going to be u of t minus 2, because the constant in the exponential function is 2, which is a is always the constant in the exponential function. So this is u of t minus 2, and this is going to be multiplied by f of t minus a certain constant a, and the a is constant in the exponential function. So this is going to be f of t minus a, in this case is 2, the constant in the exponential function. So this one is the Laplace inverse of this, but we do not know what f of t minus 2 is. To find f of t minus 2, we will have to find f of t and then shift the variable t by 2. So f of t is the Laplace inverse of the remaining function, the one without the exponent. So f of t is the Laplace inverse of what is remaining. What is remaining is 1 all over s into s squared plus 2s plus 5, like this. So when we find f of t, then we can shift f of t by 2, and that will be f of t minus 2, and that will come and multiply here, and then we'll get the Laplace inverse of this function, which is L2. I think that is L1. I'm sorry about that. That one is L1. That was the first one. I'm sorry about this. So this one is L1. All right. So now let's find the Laplace inverse of this. So to find the Laplace inverse of that, we will have to use partial fractions to break this one down. All right. So let's do that. I always do partial fraction in blue. So 1 over, I'm sorry, this is too long. 1 over s into s squared plus 2s plus 5. This one is equal to partial fraction a over the first one, s, plus, this is bs plus c, because the denominator is quadratic. That is s squared plus 2s plus 5. So now let's do cross multiplication. This is a multiplied by s squared plus 2s plus 5. And now s multiplied by bs plus c. And this is divided by the LCM, which is s multiplied by s squared plus 2s plus 5. Right, and this is equal to 1 over s into s squared plus 2s plus 5, like this. So the denominators are the same. So when we multiply by the denominator, we eliminate it. That implies that the numerators must be the same. So 1 is equal to, now let's expand. This is as squared plus 2as plus 5a. Right, and now plus bs squared plus cs, like this. So now let's gather like terms. So 1 is going to be equal to a plus b, and this is the coefficient of s squared. The coefficient of s is going to be 2a plus c. that's s, and now the constant is 5a. Right, so we have to find the values of a, b, and c. So by comparing both sides, we will have 5a, which is a constant on the right hand side, and that is equal to 1. The constant on the left hand side is 1, so that implies that a is equal to 1 over 5. Cool beans. Now what about the coefficient of s? Coefficient of s on the right hand side is 2a plus c, and the coefficient of s on the left hand side is 0. This one is equation, so let's call this one equation 1. The first one was equation 1, but it's already solved. Now the last one, the coefficient of s squared on the right hand side is a plus b, and that on the right hand side is 0, and that is equation 2. So from equation 2, we already find that a is equal to negative b, right? That is from equation 2. So if a is equal to negative b from equation 2, and then a is 1 over 5, that implies that b is going to be, so let me do it this way. So let me say b is rather equal to, so here b is rather equal to negative a from equation 2, and therefore b is going to be negative, but a is 1 over 5, so that implies that b is negative 1 over 5. Alright, cool. So now a is 1 over 5 and b is negative 1 over 5. We can find c from equation 1. C here is going to be negative 2a. So that implies that c is negative 2 times a, which is 1 over 5, and that is simplifying to negative 2 over 5. So now let me write our answers in a different color. So a is 1 over 5, right? B is negative 1 over 5. And then c is negative 2 over 5. Now that we have gotten a, b, and c, let's go back to our partial fractions and plug them in. So now our partial fraction, 1 all over s into s squared plus 2s plus 5. This one is equal to a over s. A is 1 over 5. So 1 over 5 over s, right? Plus bs plus c divided by the quadratic term plus bs plus c. B is negative 1 over 5, so negative 1 over 5s plus c, and c is negative 2 over 5, so minus 2 over 5 divided by c, and c is a quadratic term, which is s squared plus 2s plus 5. So now let's break this one down properly. So 1 over 5 over s is like 1 over 5 multiplied by 1 over s. Cool. And now this one, we can just do this. So minus 1 over 5 multiplied by s all over s squared plus 2s plus 5, like this, minus 2 over 5, and then we multiply by 1 all over s squared plus 2s plus 5, like this. And this one is equal to, I'm not going to write this one all along. We know that whatever we simplify this one to be, and that is going to be the left hand side. So that is 1 over 5. This is multiplied by 1 over s minus. Here, I am going to complete the squares of the denominator. We already did that. And that one is going to be s plus 1 all squared plus 4. Because this one is s squared plus 2s plus 1. We need 4 to add to 5. So plus 4, but 4 can be written as 2 squared. So this one can be written as this. We already did that earlier on. That is going to be this, minus 2 over 5 times 1 all over s plus 1 all squared, and now plus 2 squared. Cool. So this is what we have. So this plus 1 here, I have s on top and I have s plus 1 at the bottom. So this one looks like cosine, but an exponential function multiplied by cosine of something. So I have to get s plus 1 on top as well. So for me to get s plus 1 on top, I have to add 1, but I have to take it away by subtracting 1 again. So this is 1 over 5 multiplied by 1 over s minus 1 over 5. And now on top here, I'm going to have s plus 1, so that I'll conform with what I have at the bottom, but I have to take it away by subtracting 1. And I'm going to divide by s plus 1 all squared plus 2 squared minus 2 over 5. Now I have 1 all over s plus 1 all squared plus 2 squared, like this. So now let's break this one down into two different fractions. So I have 1 over 5 multiplied by 1 over s. My s and my 5 are very similar. So I have 1 over 5. Now break this one down into two fractions. That is going to be s plus 1 all over s plus 1 all squared plus 2 squared. Now this is something we know, minus 1 all over s plus 1 all squared plus 2 squared minus 2 over 5 times 1 all over s plus 1 all squared plus 2 squared. Cool. Now let's distribute in with the 1 over 5. I have 1 over 5 multiplied by 1 over s minus now 1 over 5 multiplied by s plus 1 all over s plus 1 all squared plus 2 squared. Now minus 1 over 5 as well, because we are distributing. We have 1 all over s plus 1 all squared plus 2 squared, like this. And now minus 2 over 5 times 1 all over it's not this one is not minus, so negative. I'm sorry about that. This one is going to be positive. All right, minus 2 over 5 into 1 over s plus 1 all squared plus 2 squared. So this is what we have. So these ones are similar, so we can combine them. 1 over 5 minus 2 over 5 is negative 1 over 5. So we have 1 over 5, then 1 over s minus 1 over 5 times s plus 1 all over s plus 1 all squared plus 2 squared, like this. Plus this one can be combined into negative 1 over 5. So 1 over 5 minus 2 over 5 is going to be negative 1 over 5. And now we have times 1 all over s plus 1 all squared plus 2 squared. You see that 1 over 5 is common for all the three terms. I'm going to factorize 1 over 5 out. And now this is going to be left with 1 over s minus s plus 1 all over s plus 1 all squared plus 2 squared minus 1 all over s plus 1 all squared plus 2 squared. This one is like cosine but multiplied by exponential function, and this one is sine multiplied by exponential function, right? So this one is equal to what we have here, that is this guy. So now let me write that. So 1 all over s into s squared plus 2s plus 5. Using partial fractions, this one is 1 over 5 outside, and then 1 over s minus s plus 1 all over s plus 1 all squared plus 2 squared minus 1 all over s plus 1 all squared plus 2 squared, like this. Now let's take the Laplace inverse, because this one we are supposed to take the Laplace inverse. F of t is the Laplace inverse of what we have, and after that we can shift it by 2. So now the Laplace inverse f of t, let me switch back to green. So f of t is the Laplace inverse of what we have here. So now let me go ahead and clean this one so that I can have space. So this is f of t, this one. So we are now going to take the Laplace inverse. I'm sorry about this. Laplace inverse of this, and that is equal to the Laplace inverse of everything that we have here. Cool. So now let's do that. So the Laplace inverse of this one is just the f of t, and that is equal to, now 1 over 5 is constant, so 1 over 5, then I'm going to have the Laplace inverse. Now I'm going to use the linearity property of the Laplace inverse. So the Laplace inverse of 1 over s, right, minus the Laplace inverse of s plus 1 divided by s plus 1 all squared plus 2 squared minus the Laplace inverse of 1 all over s plus 1 all squared, right, plus 2 squared, like this. So all this one is multiplied by 1 over 5 in front. So f of t is equal to this, 1 over 5. So the first one, Laplace inverse of 1 over s, is just 1, because Laplace transform of 1 is 1 over s, minus this one is like cosine, because cosine we have s all over s squared plus 2 squared. So this one is just going to be cosine of 2t, right? But the s is shifted by negative 1, so we have s all over s squared plus 2 squared. So this is cosine of 2t. The Laplace inverse of that is cosine of 2t, but the s variable is shifted by negative 1, that is s minus negative 1. and now the s at the bottom is also shifted by -1. So we have s plus 1 all squared, and then s plus 1 on the top. So because it's shifted by -1, we are going to multiply it by an exponential function which is shifted by -1 times t on top here, like this. So the Laplace inverse of s plus 1 all over s plus 1 all squared plus 2 squared is e to the -t times cosine of 2t, minus this guy, that is the sine version. So this one is going to be e to the -t, but it's going to be multiplied by sine of 2t, like this. So this is what we have for the Laplace inverse. So this one is the first shifting theorem. So let's write the f of t properly. I'm sorry. So this one is green. So f of t, this is equal to 1 over 5, and now into 1 minus e to the -t, and now cosine of 2t minus e to the -t, and now sine of 2t, like this. Cool. So this is f of t. We can find f of t minus 2, right? Because we need f of t minus 2 to complete our Laplace inverse, this one. So when we find f of t minus 2, then we can find the Laplace inverse of this guy, right? So that is what we have here. So now let's find f of t minus 2. And that is very simple. We just have to shift the t variable by 2. So f of t minus 2, replace all the t's with t minus 2, and we are done. So 1 over 5, 1, these are constants. So e to the negative into t minus 2, like this. And we have cosine of 2 into t minus 2, like this, minus e to the negative t minus 2. Now we have sine of 2t, but the t is going to be shifted by 2, like this. So this is f of t minus 2. Now we can find L1. L1, that is the Laplace inverse of the first one. So L1 is just going to be u of t minus 2. This is what we have here, u of t minus 2 multiplied by f of t minus 2. That will be the Laplace inverse of the first one. So this one is going to be u of t minus 2 multiplied by f of t minus 2. Now let's wrap it up here. L1 is going to be u of t minus 2 multiplied by this guy, and that is going to be 1 over 5 in front. Then we are going to have 1 minus e to the negative t minus 2 cosine of 2 into t minus 2 minus e to the negative t minus 2 sine of 2 into t minus 2, like this. So this is L1. Now to wrap up everything, we will now have to add L1 to L2. Cool. So this one is done now. So L1 is done, and now we have to add L2. And now the L2 was 1/2 e to the negative t times sine of 2t. So we just add this one to L1, and that will be the solution to our differential equation yt. So now let me switch to white now. So yt is going to be the Laplace inverse of this guy, which is what we found down there, plus L2, and L2 is this. Alright, so let's do that. L2 is 1/2 e to the negative t times sine of 2t. Alright, cool. So y of t, which is the solution to our differential equation, is L1, and L1 is this, 1 over 5 u of t minus 2. And now open this, 1 minus e to the negative t minus 2 cosine of 2 into t minus 2 minus e to the negative t minus 2 sine of 2 into t minus 2, like this. Then we close that. This is L1 and now plus L2, and L2 is equal to 1/2 e to the negative t times sine of 2t, like this. This one here, believe me, is the answer to this differential equation with a unit step function on the right hand side. So I leave this one to you to verify, to see whether if we can differentiate this one once and do it again for a second time and plug that into our differential equation, we will be able to get the left hand side to be equal to the right hand side. So I thank you so much for watching. If you find this helpful, give me a thumbs up and subscribe to Calculus Diaries. And if you have any question, you can leave them in the comment section and I'll respond to them. So I will see you in my next video, where we'll continue to use the Laplace transform to solve differential equation where the right hand side is a unit step function or a Heaviside function. I will see you in my next video. Bye bye.